Alright, welcome back. In this video, I'm going to go prove the theorem, the gradient and level curve. So given function f, which is differentiable at a comma b, and then the line tangent to the level curve of f at a comma b is orthogonal to gradient f at a comma b, provided that gradient f is not equal to 0 vector. So here's a level curve passing through the a comma b. Okay, and then the tangent line right there, and the gradient f, is the gradient is vector, right? Gradient is orthogonal to tangent line. So we want to prove that. So to show that the gradient and tangent lines are perpendicular orthogonal, we want to show that the dot product of gradient f and then the tangent vector on the tangent line equals 0. Okay, so this stress is quite simple, right? So first one, we're gonna set up the function surface, the function of the surface and level curve and the other things. First one, let z equals f of x comma y is not b, it's typo, be given. And then second one, consider the level curve f of x comma y equals z0. Here z0 we is chosen that the level curve pass through a comma b. Okay, so that all our points on the level curve, their z value is z0, z naught, I mean, okay, including a comma b. And then third one, we're gonna define the parameterization. Okay, vector r of t is a parameter defined by the vector x of t, the parametric functions right here, x of t and y of t. Okay, for the level curve near a comma b. So maybe from here to here, or the entire level curve, we can express that level curve or part of the level curve, including a comma b, as the parameterization. Okay, all right. So now and then let's say when t parameter t equals t naught, that parameterization return the a comma b. Okay, so in that the assumptions, we're gonna take a derivative of that surface, the equation of level curve with respect t, the parameter t. Then right hand side is gonna be 0, right? Because the right hand side is constant, so derivative of the constant is 0. So let me put this one, the derivative of z0, this is not in the left hand side. Okay, and then we're gonna take a derivative f with respect t. And then we gotta use a chain rule because the t is a parameter and then x and y are a function of t, right? So since this is not the derivative with respect x or y, this is a third variable t, it's a parameter t, right? So we gotta use chain rule. Then we find we're gonna take a derivative f, the most outer function f with respect the kind of middle function x, and then partial x, partial t, the partial f, partial y, partial t. Then we can express this one as the dot product of two vector. The first one is gradient, second one is the r prime, isn't it? Okay, so we haven't seen this one in the other lecture video proving the theorem regarding the directional derivative, right? So anyway, so we got this one, gradient f dot r prime. This is dot product, okay? R prime. What's r prime? R prime is what? Since the r vector r parameterization represent the what the level curve or part of the level curve, including a comma b. So r prime must be tangent vector on the level curve, and the left hand side is what? 0. 0 is equal to this. So dot product of two vectors turns out to be 0, that means the two vectors must be orthogonal. That's the definition of orthogonal, right? So, and then substituting t equal t naught, then we have gradient f dot r going to be 0, which implies that what? Gradient f and the r prime are orthogonal. So that's the proof.